Hello, welcome back. The title of this lesson is called Atomic Mass, and this is part 1. So we have a couple of goals in this lesson. The first one is for you to understand when you're looking at the periodic table and you see the atomic masses for each of the elements. I want you to understand what that number means and where it comes from. And so looks can be deceiving. It looks like there's a table and there's numbers and you just use the numbers. A lot of students do that and that's fine. But if you don't know what it means, then you will be missing a great deal of the richness of what's actually happening here. Secondly, we want to be able to calculate the atomic mass that are on that's on the periodic table when I give you some data. And then lastly, I want to explain at the end of this lesson what I find to be one of the most fascinating things regarding mass of these elements, and everything you know around you is made of these elements. So it's going to be in my opinion, one of the most interesting things about mass that we have learned. And that's called the mass defect. That's more of almost like a physics topic. I'm saving it for the end because I find it very important, but it is not the most critical thing, so it's sort of at the end. But honestly, it's more like the grand finale. I'd really like you to stick around to the end because it is a really, really interesting thing and it explains and talks about a lot of the concepts that we're discussing here. When you get down to it, what is mass anyway? When you talk about mass of anything, right? Let's say that you go into space far away from gravity, okay? No gravity, no planets, no black holes, no nothing, just you and just, let's say, a car. Take a vehicle into space with you, all right? And you push on that car with your hands in space. Of course, you're going to push yourself off, but you're going to also move the car along with you. Or if you were anchored to something, you would be able to push. But it will be difficult for you to move that car because it has mass. This has nothing to do with gravity. No gravitational forces acting here. It's just you in deep space with a car. But if instead you pull out a baseball, a very low mass object, and throw the baseball, then you could get the baseball to go very fast, very easily. So the concept of mass is something intrinsic to everything physical that we can touch. And basically the idea behind mass is that it's a measure of how hard it is to get something to start moving. In other words, it's a measure of how much force it takes to accelerate an object. Acceleration, remember, means when you speed it up or you slow it down. If it's at rest, if the object is floating in front of you at rest, it's not moving at all. To get it moving, you must begin to accelerate it. And so what we say is that what we kind of intuitively know as kids is that small objects are easy to get moving with a very small push. But massive objects, we often say heavy objects, but let's not use the word heavy. Let's use the word massive. A massive object has many more atoms and maybe atoms that have higher mass also. And so when we have more of what we call mass, it's more difficult to get it to move. All right. Now, there's a lot of modern research into what exactly is mass. Like, where does it come from? Why do certain atoms that we say are more massive, why do they take more force to get them to start moving? That's another can of worms for another day. People are researching about mass and such all the time. I mean, if you can figure out a way to reduce the mass of an object with some kind of invention, right, then you could build a spaceship that could accelerate very rapidly, very quickly. It's easier said than done, though, as we don't actually know exactly what mass is. But it's something that we measure, and we know that as we go through the periodic table, it's organized by atomic number. And remember, in the nucleus, it contains almost all the mass of the atom because the protons and the neutrons are in the nucleus. So as we go up the periodic table, we expect these atoms to be more and more massive because helium, for instance, has 2 protons and there's also some neutrons in there. And hydrogen has 1 proton and lithium has 3 protons and there's also neutrons in there as well. But as we get down to silver and lead and polonium and radon and gold, look at gold here with 79 protons here. Then what we have there is a lot of mass concentrated in the nucleus. So when you have a bar of gold and a bar of, helium or carbon or something, then of course it's going to take more force to physically move the gold, irrespective of what planet you're on, because it has more mass. So the mass is an indirect measure. It's a measurement of what we call inertia. When something is not moving at all and we try to get it started moving, we say, and if it takes more force to do that, we say it has more mass. So mass is a measure of the inertia of an object. The more mass you have, the harder it is to get that object to move. Now, when we're on the surface of the Earth in a gravitational field, the mass of the object also is related to how strongly gravity is pulling it down, okay? And of course, a bar of gold of the same dimensions as a bar of, carbon, let's say, is going to be pulled down more by the force of gravity. It's going to have a higher gravitational force. But the reason I started out talking about going into deep space was because the gravitational attraction of the planet has nothing to do with the mass of the object. It's totally independent. The mass is something intrinsic to the atoms that are present. And as we go up the periodic table, we have more mass. Now, when you look in the periodic table, the atomic number is listed. This is the number of protons, but there's also a number called the mass. In fact, this is called the average mass. You can also think of it called the atomic mass. In some books, especially older books, they call it the atomic weight. Now, the problem with using the word weight is it implies gravity. Weight is related to gravity. But if you take these atoms in deep space with no gravity, they still have mass. And of course, it could be floating in deep space with no force of gravity, but have mass. So the better word, in my opinion, and most books nowadays say the word atomic mass instead of atomic weight, but it means functionally the same thing. Now, there's a word here that's important. It says average mass. That is going to be the bulk of what we're talking about in this lesson, the average mass. And I'll give you the punchline now, and then we're going to go and write some things down and do some calculations. Remember that I said that every element on this table, we have the number here. This is the atomic number. For instance, oxygen atomic number is 8. That means there's 8 protons in the nucleus. But we also know that there's neutrons in the nucleus too. And we also said that there can be different isotopes of the same element. For instance, carbon, the most common form of carbon in the environment is called carbon-12. It has 6 protons and 6 neutrons in the nucleus. You can see it right here, 6 protons there. The neutrons aren't listed there, but the most common form has 6 neutrons as well. But there are versions of carbon, flavors of carbon, we call them isotopes of carbon, that have either more or less neutrons than the 6 that's in the most abundant carbon. But the problem is that as you subtract or add neutrons, the nucleus gets more unstable. We talked about why in the last lessons. It's because the positive charges there in the nucleus are trying to rip the nucleus apart. And so if you take away or add too many neutrons, it gets to be unstable, and so it becomes radioactive and it decays. So there's always one version of the most stable isotope in nature. And for carbon, it's carbon-12 with 6 protons and 6 neutrons. And it's like 98 point something% of all the carbon you would ever find. But there's a small fraction of isotopes of carbon, carbon-14, which has 2 more neutrons, carbon-13, and so on. And there's even a carbon-11 that you can find in nature if you look hard enough, but they're going to be pretty rare. But see, here's the thing. Remember, we talked about before that almost all the mass of the atom is in the nucleus. So if some of these flavors of carbon have more neutrons or less neutrons, then it's still going to be carbon. It's still going to react just like carbon does in a chemical reaction. But if you have more or less neutrons, all you've done is alter the mass of that atom of carbon, of that isotope of carbon. So when we list the mass on the periodic table, what mass do we pick? Do we pick the mass of the most common form of carbon, the carbon-12 that's everywhere? Or do we somehow incorporate the masses of these very low percentage, very rare forms of carbon that we call the isotopes of carbon? Because they all have 6 protons, the atomic number is 6. They all have 6 protons, but they can have varying amounts of neutrons, but with obviously a different percent abundance. And the way we do it is we have to incorporate all of it. So the numbers that you see on the table here are the average atomic mass. So it's somehow looking at the atomic mass of the carbon-12, the most common form, but also looking at the atomic mass of all the other isotopes and somehow averaging them together, considering their relative abundance in nature and their differing masses, to come up with a single number, which we call the average atomic mass. That's why it says average mass on the periodic table. Every one of these numbers here, 14.01 for nitrogen, 28.09 for silicon, 39.95 for argon, 58.69 for nickel. All of those are average masses. What they're doing is they're saying, here's all the different isotopes in nature, the different flavors of this atom, which are basically all of the same type, but very slightly different numbers of neutrons, and they all have different slightly different masses, and they all have different abundances. And we're going to create some kind of average that incorporates all of that information to give you a numerical number that takes into account the average mass of all the different types and flavors of atoms and isotopes that you have. So if you go underground and you take a shovel full of carbon, you're going to have some carbon-12 in there mostly, and then you're going to have some carbon-11 and some carbon-13 and some carbon-14, but it's very, very small amounts. The average mass of the whole bucket is going to be some sort of mathematical calculation of all of those masses. That's what we're going to do in this lesson. It's a lot of talking, but it's a difficult concept for a lot of students to understand because you're not really exposed to isotopes in everyday life. We don't talk about it, but they exist for every one of these elements. They're all out there. And so the masses here are the average of all of those masses of the isotopes that we have. Now, before we can show you how to calculate that, let me cover this table back up. And I'm going to have you recall something from a previous lesson. I'm going to write down the proton, I'm going to write down the neutron, and I'm going to write down the electron. And I'm going to write down the mass of each of these guys in atomic mass units. Now, we talked about atomic mass units in a previous lesson, but basically these atoms are so small and so little amount of mass for each one of them that we don't want to use grams because they're an incredibly small number of grams. So we actually invent a new unit called an atomic mass unit, and that is also the purpose of this lesson, to explain what the atomic mass unit is. We're going to get there in just a second, so stick with me. But what we said before is that the protons have a mass in this new scale called an atomic mass unit of 1.0073 atomic mass units. And the neutrons have a mass in this scale, 1.0087 atomic mass units. And the electrons are way, way less massive than these. They're very, very small. They're actually 5.486 times 10 to the negative 4 AMU. So the mass of the electron is much, much smaller than the mass of these. You can see 10 to the minus 4 means you move the decimal this place. So it's a very small decimal. It's a fraction of these. But you can see that the mass of the proton and the mass of the neutron are almost exactly the same, but they're not quite. But to a casual eye, they're both about 1 AMU, okay? And of course, since you know the mass of the nucleus, everything in the nucleus dominates everything, then the mass of the atom pretty much is equivalent to the mass of what's in the nucleus. The electrons you can almost ignore as far as their mass goes. You cannot ignore electrons from charge. I mean, they have a negative charge. That's very important for chemistry. But from their mass, you can ignore it mostly when you're talking about calculating the mass of the atom. Now, before we go on, I'm going to write down that 1 AMU, 1 atomic mass unit, is equal by definition to be 1.66054 times 10 to the negative 24 grams. So you see 1 AMU is a very small number of grams. That means move the decimal 24 positions to the left. That is going to be a very small number of grams because atoms are so small. That's why we use this relative scale, because these are almost the same. Electrons way smaller than everything else. Now we need to define a more practical. We can write down this number of grams for an AMU, but that's not real practical. We define 1 AMU. Defined. What we really want to do is we want to pick one element on the periodic table that's extremely common and that has an extremely stable isotope that is very commonly abundant in nature. And we want to pick that one to be the gold standard. Every measurement in life, every measurement we have has to have a standard. The meter, there's an international standard for the meter. You can go look it up exactly how a meter is defined, okay? You can look at the kilogram. The kilogram has an exact quantity of a substance that they have in a chamber somewhere, and that defines what 1 kilogram is. Everything else is basically supposed to be a copy of that original measurement we have. The unit of a second on all of our watches, it goes up by 1 second, but we have a very precise measurement and definition of what a second is equal to as well. For every unit we have, you have to have some sort of standard. Now you can define this AMU in terms of a gram, but that's a really small number and it's not a great standard. So what we do is we pick an element on the periodic table that's extremely stable, that's extremely common, and we use it to define what an AMU is. And what we do is we pick the carbon atom, because carbon is extremely common and extremely stable. Carbon has 6 protons, that's why the 6 is down here, as a mass number of 12 for this isotope of carbon. The most stable version of carbon is carbon-12. 6 protons and 6 neutrons, because the 12 minus 6 is 6. We talked about the mass number here. We subtract these, we get the neutrons in the previous lesson. Carbon-12 is defined to be, by definition, 12 atomic mass units by definition. 12 atomic mass units by definition. Carbon 12 is. So the version of carbon that's most common with something like 98%, 98 point something percent, that every living thing is made of, that very common stable version of carbon is defined by definition to be exactly 12 atomic mass units, because we know that this version of carbon has 6 protons and 6 neutrons, and so that's 12 particles in the nucleus, and we just say that that's equal to 12 AMU by definition. So a proton is going to be basically 1/12 of that. Okay, so 12 there. Now the problem, it's not really a problem, but it's something that I want to point out to you, is when you go to the periodic table and you look at carbon, it says 6 protons here. What's the atomic mass of carbon? It doesn't say 12, even though I just told you it's 12. See, all of these atomic mass numbers, they're all in atomic mass units, okay? But it says 12.01. Why do you think it says 12.01? Because the definition of carbon as being 12 AMU is the exact definition for carbon 12 with 6 protons and 6 neutrons. But I already told you there's other flavors of carbon as well, other isotopes. There's a carbon 14, which is radioactive. We use it for radioactive dating. It has 2 extra neutrons than this version, but it's very rare. We also have a carbon 11 and a carbon 13 with more or less numbers of neutrons. So the number that's printed on the table, the atomic mass, it says 12.01 because that is an aggregate average of all of the atomic masses of all the different isotopes, flavors of carbon out there. But the definition of what an AMU is that carbon 12 with 6 protons and 6 neutrons is equal to exactly 12 AMU. With no decimal point, it's exactly 12 by definition. Effectively, that's like having the master meter stick, the master kilogram, the master second somewhere in France or wherever it is, locked up as the master copy of what the unit is. Carbon it exists everywhere in nature. That's the master meter stick of what an AMU is. All right, so how do we then calculate? How do we then calculate these atomic masses of all of these other elements here? They're all atomic mass units, but they have to somehow incorporate all of the isotopes in nature and all of the atomic masses. And the way you calculate that is what you basically say, you call it the average atomic mass. Because it's an average. It's an average of all of the atomic masses of all the isotopes of each element, and for instance, carbon, right? And what it's equal to is the sum, and this is a Greek letter sigma, it just means add everything up that follows. The sum of the isotope mass multiplied by the fractional abundance. Right? So what basically is going on here is we have lots of different flavors of carbon, but each of them have their own mass because they differ by the number of neutrons, and they each have their own fractional abundance. And what we do is we take what we call a weighted average. So we take the mass of each isotope and we multiply it by how common it is in nature. Some of these things only have like 0.01% abundance. They don't count for much of anything. They're just so rare. So when you multiply by the fractional abundance, you basically scale the final answer by how common some isotope is. So to really see how this works, it's going to be much, much easier to talk about an actual example. So let's go over here and let's talk about 2 of the isotopes of carbon. So there's a carbon 12 and there's also a carbon 13. Now there's actually a carbon 14 and there's some other isotopes of carbon, but this is enough to get the point across. So carbon 12 is exactly 12 atomic mass units, and it exists at something like 98.93% abundance. Right? And then this other version of carbon, which has 1 extra neutron because the mass number is 12. Remember, they all have to have 6 protons. So I can put the 6 protons down here. But that's true of any version of carbon. Okay. But this guy has for this one here, the atomic mass of this one. If this is 12 AU and we've added a neutron, this is a slightly larger 13.00335 AMU. It's about 1 more, right? Because we added 1 more neutron. And remember, a neutron is just a little bit more than 1 AMU. And so we added 1 more, and so that's what it is there. and then it is at a percent abundance of 1.07%. So again, there are additional versions of carbon out there, but they're even smaller percentages. So they don't contribute very much to the total mass. How would we calculate the average atomic mass with just these two pieces of information? What we would say is we would take the first one, we would say 12, and we would multiply it by this percentage, but you don't want to use 98, you want to use 0.9893. You want to take all percentages and convert them to decimals by dividing by 100, moving the decimal 2 spots to the left. So when you multiply this, you're almost multiplying by 1, and you're weighting the answer to be very close to 12 because most of the carbon has a mass of 12. But then you're going to add to that this version of carbon, this isotope, 13.00335 AMU, and you're going to weight it by 1.07%. You move the decimal 2 spots to the left. 0.0107. You always in math, when you deal with percentages, change them to decimals. Never multiply by a percentage as a whole number. You always move it to a decimal equivalent by sliding that decimal 2 spots to the left. So it's 0.0107. Now, when you do this calculation, when you multiply these numbers together, you get 11.8716. See, that's very close to 12 because you weighted it so high. But then this one, this mass is much, much higher than this one, but it only counts for a very small fraction in nature. So when you multiply these out, it comes out to 0.1391. And so the total mass, when you add them together, this one counts as a very small fractional increase, right? And so when you take this number, 11.8716 plus 0.1391, and you add them, you get 12.01 when you round it to 2 decimal places. And what we're saying is that this is the average atomic mass of carbon. And then if you slide over to a periodic table and you take a look at carbon, you see we get 12.01. That's why it's 12.01. Because you have a most common isotope that's like 98% or 99, almost 99% at exactly 12 AMU. So that weights the average atomic mass very strongly in that direction. And then you have these other isotopes which are heavier, sometimes lighter, but they count for less because they're not very common. And you add them all together. So when you look at an equation like this, it looks like really complicated with the big fancy sigma. But all it means is you're just taking the mass times the fractional abundance, and then the next mass times its next fractional abundance. And you do that for as many as you have, and you add them all together. Now, I want to emphasize that we only counted 2 versions of carbon here. There's actually a carbon-14 with an even smaller percentage, and there's other versions of carbon with smaller percentages, but they're going to contribute to the average atomic mass very, very, very slightly because they're so rare in nature. So you could do the calculation again, but it's not going to move off of 12.01. You'd have to carry more decimals out to see any difference there. All right, so what I want to do is do the same calculation with another element to show you one more time how this works. All right, so there we did it for silicon. I'm sorry, for carbon. Next, we're going to do it for silicon. All right, so let's take a look at silicon. We have lots of isotopes of silicon. We're going to talk about silicon-28. That's a mass number of 28. We're going to talk about silicon-29 with a mass number of 29 and silicon-30 here. Now these numbers, remember, these are mass numbers. All of these silicons have the same atomic number. Silicon, where is it at? Here, atomic number 14. So you don't have to write it down, but all of these silicons have 14 protons in the nucleus. All of them do. But because the numbers are different on the top, they have a slightly different number of neutrons, okay? And the way you figure out is you subtract. So this one has 14 neutrons, 28 minus 14, and this has 15, and this has 16 neutrons when you subtract the numbers. Now, what we're going to write down, I'm going to give you some data. I'm going to tell you that this version of silicon has an atomic mass of 27.97693 atomic mass units, and it's 92.23% abundant in nature. This version of silicon with an extra neutron has a mass of 28.976495. Notice it's just about 1 more AU higher because we added only 1 more neutron. But its abundance is only 4.67%, very small percent abundance in nature. And then we have silicon-30, which has yet 1 extra neutron from here, so 2 extra neutrons from the most common, and this is 29.973770 atomic mass units at a 3.10% abundance. Now, I haven't checked, honestly, but there are probably more isotopes of silicon as well. So you got to cut it off somewhere, right? Because you have some isotopes that can be extremely rare, almost to the point where they're almost never found on Earth, right? But for this calculation, this is good enough for us to see how this atomic mass thing works, how this average atomic mass calculation works. And what we do is we calculate the average atomic mass as follows. What we do is we take the mass and we multiply by the percentage. So it's 27.97693, but we never use this. We slide the decimal 2 points to the left, 0.9223. And of course, because we're multiplying by almost 1, then the atomic mass is going to be very close to this because this is the most common one in nature. But then we have to add to that the next atomic mass for the next isotope, 28.976495, and then we're going to multiply that by this. We slide the decimal 2 to the left, 0467, 2 spots to the left. All right, and then we add to that the last one, which is 29.973770, and we multiply that by its abundance, 0.0310. Like this. So you see how these masses are heavier or they're higher because they have extra neutrons, but they don't count for as much because they're not in nature as much. And so when you take this number times this one, and this one times this one, and this one times this one, and then you take all of those and add them together, after you multiply first, then you add the results together, what you get is 28.09 atomic mass units. And before I do anything else, let me just check. 27.97693, 28.976495, 29.973770, and then 0.9223, 0.0467, 0.0310, and we get a mass of this for silicon, an atomic mass of this for silicon, 28.09. We go to silicon, we get an answer of 28.09. That's why that number is printed on the periodic table, because it is an aggregate average of all the isotopes in nature. Again, there could be other isotopes with even smaller abundances, but it's only going to affect very small decimals. So, you don't have to, if you want the true correct answer, you got to use them all. But for the purpose of illustrating what this is about, using 2 or 3 of the most common isotopes is good enough. So that is the concept of atomic mass. That's the concept of average atomic mass, and that is where these numbers come from on the periodic table. The top number is the atomic number, the number of protons in the nucleus. Here is the atomic mass, the average atomic mass across all the isotopes that exist in nature, including their fractional abundances. Now, we have that out of the way. We need to do that. We needed to get that off we needed to show you where all that comes from. We're going to do some more problems with that. Now what we want to do is turn our attention to what we call in physics and chemistry mass defect. Now, in truth, I don't really have to talk about this, because most people probably won't even realize that it's a thing. And so I probably would just go, I mean, when I first learned this, I didn't realize that this was an issue. But scientists, of course, have realized this is an issue over the years, okay? And it's something that we have explained, but it's something incredibly fascinating. Basically, mass defect, again, it's more of a physics thing, but it's, I don't want to leave you hanging on some of the most interesting things we can possibly learn, so we're going to throw it in here, then we're going to solve our problems. Now, what we said in the beginning, I kind of glossed over it, but it's actually something that's like kind of a showstopper when you think about it. What we basically said is that 12 atomic mass units was defined by our gold standard to be not all carbons, but only carbon-12, the most stable form of carbon. We just say that that's equal to exactly 12 atomic mass units. And we know that a carbon-12 has 6 protons and 6 neutrons in the nucleus. Okay, so let's go over here and look at our table that we wrote down. These are the tables of the masses of all the protons and the neutrons and so on. So we know that we should be able to have 6 protons in the carbon, 12, and 6 neutrons. And when we multiply this times 6, and we multiply this times 6, and we add them together, we're going to get something bigger than 12. But we said that carbon-12 was equal to 12 atomic mass units by definition. But when you look inside the nucleus and recognize that there's 12 total particles, 6 protons, and 6 neutrons, and use the masses that we have given in this table and actually add them together, then you get a mass more than the 12 atomic mass units that we say is the defined standard for atomic mass units. How can it possibly be that you know the masses of all the protons and you know the masses of all the neutrons, but when you add them all up, you get something bigger than 12, but yet when you look at the standard, it says carbon 12. We're not talking about isotopes or all the other versions of carbon, just that one version of carbon, carbon 12, with 6 protons and 6 neutrons should have a mass of exactly 12. Not a little bit more than 12, not a little bit less than 12, exactly 12, because it's the standard. It's defined to be 12. So how can it be when I add up 6 protons and 6 neutrons and add them up, I get something bigger than 12? Well, that's something called mass defect. It turns out, and this again is more of a physics thing because it doesn't really affect chemical reactions, but it's just one of the most interesting things that I know and that I think we all know as humanity, right? So here it is. It turns out that when we look at everyday experience, if I've got a bucket of grapes, let's say, a bucket of grapes in front of me, right? Then I know that if I measure the mass of every one of those grapes and I add them all up, then I should get exactly the same number of mass, or the exact same mass as all of the grapes when they're inside the bucket. If I subtract the mass of the bucket and just look at the mass of the grapes all together, and then I know the mass of all individual grapes separately, I should be able to get exactly the same number down to the infinite decimal point, infinity decimal points, because everything in the bucket is exactly, they're the same thing as outside versus inside. But actually, subatomic particles don't quite behave that way. We know the masses of the protons and the neutrons, and the electrons, let's ignore them because it's so small. We don't care about those right now. But the protons and the neutrons, we know the masses of them very precisely because we do experiments with individual protons, and we have ways of measuring the mass of the protons and the neutrons. So we know them very accurately. But when we go to a carbon atom, and we know the carbon atom has 6 of one and 6 of the other, the mass is always less on the inside of the nucleus when they're bound together than the sum of all the individual protons and neutrons that make them up. Let me say that one more time, because if you're not careful, it goes in one ear and out the other, and you're like, who cares? Listen to what I'm saying. We know the masses of protons and neutrons. We can do very accurate experiments. We know what they are. You should be able to add them all up, right? And figure out the mass of a nucleus of any atom you want. However, when they come together and form a nucleus, and we measure the masses of those atoms, when they come together, the mass of the nucleus as it's bound is always less than the sum of all the protons and neutrons that it's comprised of. And that is called mass defect. That's exactly what it's like. People basically did experiments to measure the mass of protons and neutrons, and then they did experiments to measure the mass of carbons and silicons and all kinds of things, and they always found that the mass of the individual atoms when they're bound together like that is less by a small amount, a very small amount, than the mass of the individual particles. And that's what's happening here. If you add these together, 6 times this and 6 times this, and add them up, you're going to get something bigger than 12. However, when we measure the mass of carbon, we define it to be exactly 12, but the sum of everything inside of the nucleus is more than 12, because when everything comes together and is bound in a nucleus, its mass is less. Now, you're scratching your head and you're like, he's telling me this, but how can this be? Because mass is a constant. Mass is fixed. Mass is mass. It doesn't change. Even if I burn the thing, it turns into carbon dioxide or something, but it's still there. All the atoms are still there. How can the mass in the nucleus be different than the mass of everything when they're separated, when the protons and the neutrons are separated? Well, there's a famous equation that you might know, and it's called E equals mc squared. This equation, of course, you all know is Einstein's famous equation, and this actually isn't even the full version of the equation, but it's good enough for what we're talking about here. What it basically says is, forget about the speed of light right here. We have a mass on one side and energy on the other side. What it basically says is that mass and energy are interchangeable versions of the same thing. If you think about liquid water, and you think about solid ice, and you think about water vapor that's in the air, those are all still water molecules, but they're different ways and different manifestations of the same thing. Solid, liquid, gas are different phases of the same molecules. We now know this. Of course, we didn't know this 300 years ago, but we know this now. And now we know that mass, the thing that we call mass, the thing that we call hard things that we can bounce our hands on, that's something we call mass, right? The thing that resists our push of motion in space, that's mass. It can be exchanged and turned into energy, and energy can be exchanged and turned into mass. and we look at nuclear reactors, either nuclear explosions or nuclear reactors, we can change mass into energy, and energy can be changed into mass. And this is the equation that does it. The speed of light squared acts almost like a conversion factor. It's a conversion factor that tells me how much energy I have when I have a certain amount of mass. In fact, if you put 1 kilogram in this equation for m, speed of light is a very, very big number, 3 times 10 to the 8th meters per second. This is a big number. The speed of light is 3 times 10 to the 8th meters per second. That's a huge number, but it's squared. So this is an even gigantic number. If I multiply by 1 kilogram mass like I can hold in my hand, then it's an enormous amount of energy. What it's saying is that every piece of matter around you contains an enormous amount of equivalent energy. But that energy is kind of like condensed, for lack of a better word, into what we call mass. You think about water vapor, you can condense it and make it into liquid water. And then that liquid water, you can think of condensing it sort of and making it into a solid version of itself. And the difference between them is basically the temperature, right? Well, matter is sort of like a condensed version of energy. You can change one form into another. So that's an aside, but that is the explanation for why when we look at the masses of the nucleus of the atom, we always get something less than the sum of the protons and the neutron masses. Because when things come in and form a nucleus, when they're far away, they're at a higher energy. When they go in and they bond together and the strong nuclear force takes over and they get sucked in and they go down and form the nucleus, they basically go to a lower energy state. So basically, originally, when everything's far apart, the energy is higher, right? But then whenever things come into the nucleus, they go into a lower energy state, right? And so we go from a higher energy to a lower energy state. Where does that energy go? Well, if I take some object like this marker and it's higher off the ground, it's at a higher energy state. When it's closer to the ground, it's at a lower energy state. If I let it travel from point A to point B, where did its energy go? It got converted into kinetic energy. The energy of the potential being higher here and lower here, whenever it traveled through the path, it changed its potential energy into kinetic energy, into motion. That's what happened as it traveled from one spot to another. But in an atom, whenever the protons and the neutrons come together, they're in a higher energy state, and they also become into a lower energy state in the nucleus. Where did the energy go? In here, it went into the motion of the object, but in an atom, the energy comes from the mass of the protons and the neutrons, and it goes into what we call the binding energy, the energy of the attractive force, of the strong force inside the nucleus. So the reason why we take protons that are all separated here and we make a nucleus and then the mass of the nucleus is lower is because as they get accelerated in and they get attracted in by the strong nuclear force and they form a nucleus, they go to a lower energy state. That energy has to come from somewhere. It's not going to go into motion of the pin like this large example here. The mass goes and comes from, the energy comes from the mass because mass and energy are equivalent. They're different forms of the same thing. The energy has to go down. It comes from somewhere. It comes from the mass. And it goes into the binding energy of the atom. If you think about it, it takes energy to break apart the nucleus of the atom. So once you have an atom formed, you have to put energy into it in order to break it apart, right? Because everything's attracted really, really strongly by the strong force. You'd have to put energy in to pull it apart. So when things come in together to form, there must be energy taken from someplace, and it comes from the mass of the neutrons and the protons. And it goes into the binding energy of the actual nucleus. Now, I did a lot of talking. I didn't write any equations other than E equals mc squared. This topic is quite complex. I have grossly simplified it. I have overlooked so many things that you might as well say, why did you even mention it? Well, that's because education is a series of lies, is what I tell you people all the time. You know, I'm telling you a top layer of what's going on here. Yes, it's true that the nucleus mass is less than the sum of the protons and the neutrons. True. And it is true that the mass is changed into energy, goes into binding energy. But when you study this for a living, which is not my actual area of expertise, there are entire people that deal with nuclear reactors and fusion and fission, that this is what they do every day. And there are a lot of details missing from what I'm telling you. But the gist, the overall framework of what mass defect is there. Now, is mass defect important for chemistry? No, it's not. It's really not. It's useful and important when we're talking about nuclear physics. However, we are talking about nucleus. We're talking about protons and neutrons. We're talking about electrons. So why not talk about one of the most interesting things that we always take for granted, that the mass of something is the sum of its parts, but actually in a nucleus of an atom, it's not true, because mass and energy are different manifestations of the same thing, basically. All right? And the most important thing from this lesson is that this atomic mass, which is printed on every one of these things, is the weighted average or the weighted sum of all of the isotope masses that are in nature. I just wanted to point out to you one of the most interesting things that I find, which is that, hey, why does a proton have more than one AMU? Why does a neutron have more than one AMU if the atoms, when you add them all together, have a smaller mass? Like, shouldn't carbon 12 have a mass bigger than 12? Well, yes, but when you put these things together, some of their mass gets changed into energy, which is the binding energy of the atomic nucleus. That's where it goes. Mass is converted into energy, the binding energy there. So watch this a few times, and hopefully it whets your appetite so that as you study more, you'll want to learn more and contribute more and discover the next big thing. That's what I'm hoping for, right? And I want to shield you from the most interesting things that are out there. So make sure you understand this. Follow me on to the next lesson. We'll come back down to Earth and start doing more calculations with average atomic mass.